Okay, so similar to a switch, there's something called a relay, which drawn like so. The box. Electrical engineers love to draw boxes. Okay, they label this solid state relay. So what these do is it's comparing, right, like a comparator, VCC to your I/O, which is your input or output, also a digital signal. If it is on, in this case 0, it closes a switch, right, closes mean it connects, a switch internal to the relay. You do this when you have a lot of current, right? These semiconductor devices don't deal very well with high currents. They don't deal with anything over an amp, really. So if you're trying to drive something like an electric vehicle, right, you're not going to have a switch that is on or off. You're going to have a solid state relay, because that way you can have tons of current flowing through without actually damaging the device that is doing the control. Another important device is, right, we've talked about inputs. Now we need to get data out of the system. These are called D2As, digital to analog converters. They're going to look, again, we're going to draw a box, because we always draw a box. And it's going to say, this is just going to be a nice 4-bit, and it's going to have 4 digital inputs, and it's going to output some analog voltage. So it's going to have numbers here, which is nice, compatible with your digital system, and it's going to output analog voltage. That's how you go from digital system to real world. Now this, the digital to analog converter, is actually also going to have some levels. It's going to have a resolution. The solution then is, and unfortunately the ordering in this class is a little bit weird, you can do what's called low-pass filtering. Just so you're aware, it's a circuit that looks like this. Where this is a resistor, we're familiar with those. This is a capacitor, you're less familiar with those. They store energy. And when you put the voltage into that circuit, this takes away some of the high frequency components. Does everyone know what the word frequency means? So, low frequency would look like this. The sine wave that changes. A high frequency would do the exact same thing, same amplitude, but it does the sine wave faster. That's high frequency. So in order to make a step like that, that's very high frequency to do that. So this gets rid of high frequency components, and so instead of looking like this staircase, the output of that will look more like that. It's kind of like an averaging filter. So this D to A, in output levels, a lot of times you'll filter it to make it look a little bit smoother, and that's how you interact with the real world. It's common, again, to have, this is drawn as a 4-bit, it's very common to have 8 to 16. I think I've seen as high as 24 or even 30, but it gets really hard after that. Something that the book says is outside the scope of this class that I think is really interesting, because it's my wheelhouse, is how do you make digital to analog converter. They're actually really simple. You can make way more complicated ones that are more accurate. We call this one, though, an R2R DAC. Should I stick it just that bit? Keep it simple. And we're going to start with 0, 1, 2, out. And this is all it really is. So your bits, your digital data, comes in through these. They're either 1 or 0, right? And you can do some fancy Ohm's law calculations, which I won't make you do, to show that the output voltage, if all of them are 1, ends up being high, whatever the digital logic is. If they're all 0, it ends up being 0 because there's no power supply. And every step in between, as we count, I erased the number, right? Every other digital combination outputs some voltage level between 0 and your supply voltage. So it's just going to step up. That's all it is. That's all a digital to analog converter is. I wanted to show you the inner workings of it because the book and the homework does care about how that works, and your V out is going to equal to the reference voltage I don't like this notation, but we'll stick with book notation. It's going to be Vref times the DAC input divided by the number of bits. And Vref is the voltage that you're targeting, right? So that if your DAC in is 111, the maximum voltage, it's going to be just Vref, right? Because you're going to have 2 to the n by 2 to the n. So we're going to do an example. Don't worry, I won't leave you hanging on this one. So let's say we have an 8-bit DAC. And Vref is 4 volts. This is a silly example because nobody uses 4 volts, but let's go with it. How do I calculate V out if the DAC number is 144? Well, we use the equation. Vref, 4 volts. Let's start with the denominator. What goes on the bottom?
2, 8.
Yep. What goes to the numerator? Yep, just 144.
What is the 144? Is that like a voltage, or is that the number? Like, is that a binary number?
It's the decimal representation of a binary number.
Oh, okay.
So you could go. We could go through this, convert it to binary, and look at its bit code. I don't actually know what it is, right? And then figure out what that would look like to your logic system. But it is entirely possible in modern logic systems to program in decimal. And the synthesizer, which is like a compiler for code, will take the decimal and turn it into binary. So in this case, 144 is sufficient because we know it's the 144th code. Remembering that it is 0 indexed. You start counting at 0. Let me flip through here. So that's chapter 3, which is all nice and straightforward. We're halfway done. Okay, we're doing okay. Do we have any questions on Ohm's law, switches, diode connections like we did in the lab? Any questions about lab 2? Or lab also is what I meant. Now we're all good? Okay. So chapter 4, we're diving into what we call Boolean logic. Boolean meaning ones or zeros. You'll also hear me, and I'm going to say this up front, normally this is vocabulary for later, call something of states, right? We're going to introduce this as Boolean states, which is, the example they are using is a washing machine. Super interesting, right? Okay, so what their whole point with the washing machine is you could have situations where you're washing your clothes and you either want hot water, warm water, or cold water. And if it's hot water, you're going to have some state that you're going to have a 1, a high, that says, hi, I want hot water, right? And cold water might be the 0, which says 0, I want cold water. Warm water is this mixture between hot and cold, which is neither 1 or 0. So we have to add another bit, right? And each of those, so 1, I want hot water. 0, I want cold water. But if I need more than that, I can then modify this. Let me change this a little bit. Using our binary counting, that if it's 0, 0, it's cold. Now I'm going to jump all the way up here and say if it's 1, 1, it's hot. And these middle states are going to be, could be 2 potential levels of cold water, right? So this is, let's like 40-60 ratio, and this is a 60-40 ratio, right? Getting hotter and hotter as we go on. So that's what I mean when I say Boolean states. I do recommend reading through chapter 4's introduction and just that intro level of 4.1. It's going to give you kind of a more hand-holding walkthrough than I just gave you. But that's what this digital system is doing, and there is a simple little digital system inside of your washing machine, if you go to laundromat, whatever it is, where you're pushing those configuration buttons, and it's obviously going to have more options than that, but ultimately your washing machine might have, right, it's going to be how hot is the water, you want the extra rinse cycle and all those other little settings, and those are just going to add some more of these options, more of these states, and that's going to go into some logic, which we'll learn how to design throughout this course in order to make those decisions into the buttons into reality. So we start getting this idea I think I introduced this a little bit in passing in a previous lecture of truth tables. So we have this idea of logical operators. They are, do you guys mind if I erase this? Good. And they're most basic, and or. Things are anded together or ORed together. Now there are lots of other options, but let's start with these two. So A and B's, we might be saying, right, in those digital states, that one of these is a logical high and one of these is a logical low. But let's just count through. 0, 0, 0, 1, 1, 0, 1, 1. Binary counting, we're going to do a lot of this. Now C is some output, and we're going to compare this. So we're looking for A and B, and we're checking to see if that's true. So A and B, no, neither one. So that means the output is not true, 0, false. This is also not true, right? Because it's a 0 and 1, but it's not 1 and 1. Repeat. But look, now we've got 1 and 1. It is now, that's a very large 1. This is now true. That's what we mean by and. 1 and 1 is true. We can also do the same thing for OR. Is this a 1 or a 0? 0. Yeah, it is not true. How about this one? 1. It is true because one of them is. This one? How about this one? It's also a 1. There is another logical operator that we call exclusive OR. Or XOR, where this is not true, because it's exclusively one or the other.
So is that it? We have and, or, and XOR, or is there more?
There is more. One of the most simple ones, not, right? And that's simple. That's a simple truth table because it doesn't have multiple inputs. It just, the output does the opposite of whatever the input is. And XOR. Can anybody else name other gates? NAND. Yeah. We also have NAND and NOR, which just means not and, not nor.
So it's like the inverse of and?
Yeah. Yeah, it's just literally taking not this. And actually, that's a good segue. So good question. Notation for that, if I don't like it, put a bar over it. So that is, to have A and B, C, not C, and I just do the opposite. So we have NAND, NOR. You can actually also do XNORs. So this not operator, this bar, we call the complement. It's the inverse of what is true. And we're going to go through some fun stuff later on this semester dealing with the complement because it ends up being very useful. Because if you're trying to design logic and you have an LED light, right, and you want the light to light up in a certain circumstance, but you've designed logic that it's on when 1 and off when 0, it's easy to develop the complement to that logic to flip that when it's on and off. And we will learn how to do that. Now, these logical operators have symbols associated with them so that we can move towards Boolean algebra, because everybody loves algebra. So and is multiplication. So if I want to write and, A and B is equivalent to that. Now, don't get confused, because or looks like a plus, which sometimes we say A and B, but it's not. In logic, Boolean algebra, the plus sign is our or. And is multiplication. But the nice thing is, doing it this way, because the way the logical operators work out, if I have some equation of D is equal to A and B, or C, which operation happens first? The and, yes. So the and takes priority over the or, unless you have parentheses, just like in algebra. So you could do B or C and A. And then you can start drawing out a truth table for that, right? So let's take that truth table. I'll just do a couple of these. I don't think I'll walk through the whole mess. And something like that. Okay. So we can do a couple of things, right? We've gone through the and we know that A and B, in order for that to be true, both of these have to be true, right? Both the A and the B or C, right? So if we look at A, we know A has to be true. So we know that all of those are 0, right? 0, 0, 0, 0. Now let's look at this. What is this one? 0, yeah. Because now we're looking at B or C, which is not true. What's this? 1, exactly. Because we have the B or C here, which is true, and we have A. That makes sense for everyone. Other notation, just so we're aware, if I'm writing on the board, I will almost always use C bar example as the complement. If I'm writing it in text, it will almost always be C apostrophe. If I don't say C apostrophe, I say C tick, because tick is faster to say than apostrophe. That comes from like old programming language, but the book also points out that they'll do the tilde. There are some programming language they use the exclamation mark. Similarly for this, I can say not B or C. I can put the bar over the whole thing, right? There is a big, long example in section 4.1 that I would actually recommend kind of walking through that example on your own. It's not complicated. It's not any harder than what we did here, really. And it's just kind of getting in the habit of writing ones and zeros. All right, kind of watch the time to make sure I don't go over, and that clock is weird. Actually, we're going through really quick. There is one other symbol that I'll bring up so that we're aware. Remember how I said there's the XOR? That symbol is that. Those are really the three symbols that you four, because you need to know the that was embarrassing. All right, complement, the inverse, right? Complement is inverse. And, which is just multiplication. So this is also valid. Little dot, right? That's and, or you can just leave it off, whichever you want. Or being the plus, and exclusive or being the plus and circle. For now, that's like the main symbols that you need to know. Let me look through this next section. I actually did not think I would make it this far today, and we've still got, what, half an hour left, almost? 15 minutes. Oh, that's not too bad. I'm still getting used to how fast I teach these things, so I don't feel too bad about ending a little bit early. I'm going to look through this next section briefly to see if I can cram it into your heads. So this is a really simple section, so it really starts out as such. If I have let's do it 8. We deal with 8 bits a whole lot. A lot of that comes from because it's a nice round 2 to the 3, right? And it doesn't quite get out of control yet. It's pretty easy to write truth tables for 8 bits. The other reason is because ASCII, which is the character encoding for all letters and numbers on your keyboard, are 8 bits. And so we'll stick with 8 bits. Now, this term is the most significant bit, right? It's the biggest one. We talked about that last time. Similarly, this is the LSB, the least significant bit. Man, I skipped ahead. So we've done some of these truth tables. So there's a new term, new definition that we're going to bring in. Back to the and, right? So this term, this row, is what we call a min-term. And a min-term is, by the big definition, is a logical expression that is true. So one's being true, for one and only one row of this truth table. Right? So this has one min-term because it has a 1 in it. And it is true in that row. That row is true. So A and B being 1 is a min-term. The complement of that min-term is 0. You can start having big truth tables that there is on page, it's figure 4-5. I don't have pages in my printout, and that's troublesome. So it uses a more complicated truth table that goes through A, B, C. And this is what I mean why we use 3 bits all the time. Because it's easy enough to write, while complicated enough to get the point across. And then on this side of the table, we're going to show various operations. So for one of these, not A, not B, not C. Quickly run through and write down what that truth table ends up being. Hopefully you're all done. Yes, because the situation in which we're not A, not B, and not C is only that one, right? Every other case, we have at least one of those. So that's zeros. Similarly, switch it up, and if we have A, not B, C. Where do ones go?
A and C.
Yeah, so when we have A and C, but not B. Boom. Right? Nice and easy. I think I'm going to call it there, and we'll pick up with some of these min-terms, and we can start using truth tables next time to start writing logical equations. So I can start describing a function. So if I have a truth table, and I'll give you just a little sample that looked, we'll ignore these. So this is how you do the opposite direction. This is would be a really messy one because look at all those ones, right? The fewer ones there are, the simpler the expression is generally. And I would start writing one at a time, like D is equal to, well, I have A, B, and C, or, oh, sorry, those are all not it, you're right. Right? So we're starting to be true when not A, not B, not C, or not A, not B, C, or, right? And I'm going to have or terms for every single one of those. On the flip side, I'll make a note to review this at the beginning of next class, but I want to get this into your head because this is kind of like the big takeaway. I can do the opposite. So this is the sum of products. Stops. Or I can do product of sums, which is the flip way, and start anding things on the zeros and take the complement. Anyways, that's class. Thanks for coming. I'll see you all in lab in an hour and a half or whatever it's up.
So I've got, I don't have my lab, like, book yet. I ordered one that's bound, so I thought that would answer for me. So can I just use a sheet of paper? It should be here.
Okay. So, I'll be forgiven for you.
Awesome. And I just, so to submit our lab, I just scan mine and
Yeah, I would like them scanned online.
Okay.
It saves so much time.
Right. Awesome.
I would like you to scan it, take a picture, and upload it online. Yeah, no, I would like them online just because they're.
Other engineering teacher said she wants them.
Hey, did you, I got a question. You went and bought, you buy those, blankets?
I'm trying to ride the wave of the future where everything is digital.
So, on the homework, there was a question that was like, so whether it says analog or digital, it's like stoplight, stock prices.
Yes.
Stock price is digital because it's a computer, so it's 0 and 1.
Yes. There's actually two reasons that it's digital in modern times. So part of it is exactly what you just said. It's because it has to be transmitted to somewhere digitally. The other part of it is that unless you start getting weird, you don't deal with partial cents, right? It's $4.51. You typically don't get into $5.51.00000 forever. There is some cutoff. Even if you start dealing in penny stocks, which have like partial pennies, it stops somewhere. And if it ever stops, it's digital. I feel like they designed that one as a trick question, if I'm perfectly honest. But.
Oh, you're good. You got plenty of time.
No, I'm going to try, if people are walking in, I'm going to start spraying off where people
Like,
are.
stoplight is
There's a class.
digital signal.
I feel like this is like,
Yeah, analog signals can last forever.
freaking.
Yes, that is also something. Yeah.
Oh, man.
Yeah, and I honestly, I feel those aren't my questions, they're Dr. Brown's. And some of them I feel they're tricky on purpose, right? Because a stoplight is, well, a light is obviously analog because it's a real world thing, but the state of the light is digital, right? Because it is either red, green, or yellow.
So for that specific question, it's a digital signal.
Yes, because what is transmitted to you is digital information.
So these chairs are so spaced, and these chairs are slammed.
That's the only question that really
room of your table.
They used to be 3 chairs and 4 chairs, but I don't know.
was a little confusing for me.
Yeah, no, I don't blame you. And that's why if I were going through all of this, it's a new way of thinking. Digital logic is just a different way of thinking. It takes some time to get used to it.
Yeah, we'll see in a little.
Yeah, see ya.
Not how people do it, right?
What is this, 2700 Lecture3? Yeah.
So you're doing both the digital ones pretty much.
Yes.
Do you have any other classes or just that there?
No, I have 2 sections of systems and 1 of circuits.
So that's usually a spring class, right?
I don't know. I'm still getting used to the
I had
system.
it spring when I was like, oh no, I think it's usually a fall one. I don't know.
Digital systems we took how long ago? 2 years ago?
I took it spring, but I don't know when it usually is.
I think we're trying to get to the point where 2700 can be offered both.
I know they wanted you to do that with engineering 1010. What is it?
Well, 7.
Well, 17, there it is. Yeah.
The plan I heard was they're going to do 2 sections, like the time when you're supposed to take it, and then 1 section the time when you don't. They're like,
Some of that, yes. We're still in flux. We're trying to make it possible, because we're weighing the needs of the faculty versus as well as students.
You only have so many professors, right?
Because we only have so many professors, and if I were to say teach digital circuits, digital systems, and VLSI in a semester, that's 3 classes I have to prep for. Right now, I'm taking 2 of digital systems and 1 digital circuits. There's only 2 classes I have to prep for. And we have the added benefit if we can offer that as night classes. So I think the goal is to ramp up because at least me, I'm fighting for, I like teaching 2 of the same course. So we'll offer more and more night classes of the junior level, so you can get through up through the junior level in almost all night classes without ever having to wait for it, at least not more than a semester.
Yeah.
But it gets complicated by the fact that we have barely enough faculty, and we're also trying to ramp up the master's program.
Oh, yeah.
Because we want to get some really good classes in the master's. I intend on teaching in the fall or spring sensor systems course.
Hello. How are you?
I'm good.
So are you guys still finishing something up?
No, we're just chatting.
Okay.
Yeah, no, we're here really early for our class.
Cool. You guys are in Fawn Brown stuff?
Yeah.
Cool.
So we're probably
Listening to your lecture is my guess.
Yes.
Let me log out of this.
No problem. Are you one of the new faculty members?
I am.
Awesome. I'm Diana Meiser. I am the librarian for this college. Let me give you my card.
Thank you.
You're welcome. So if you ever need anything from the library.
Okay, that's good to know. I actually probably will.